So I think before I start, I'd really like to thank Panos for organizing this talk, and also I'm actually here as part of a Bath UNAM SciMath workshop, and I think he's also the local organizer for the workshop, which will be on Thursday and on Friday. So can you all hear me properly? I think you can. So first and foremost, I'd like to thank Panos and the team at IIMAS for organizing this event. So as you can tell from my title, I mainly work on nematic liquid crystals. I work on the mathematics, the modeling, and the modeling of liquid crystal, nematic liquid crystal applications. So when Panos suggested this talk, he said that I should assume no knowledge. So I should assume a non-specialist audience, and therefore I'll be telling you everything that you need to know for following this talk. So I'll be assuming no background knowledge, which I think is a good thing. And hopefully at the end of the talk, I will be able to convince you that this is actually an exciting area of research to work in. So the talk is organized as follows. So I'm just going to start off by telling you what liquid crystals are, assuming that perhaps most of you do not work on liquid crystals. I'll tell you a bit about the history. I always think that's interesting for a general talk. I'll tell you a bit about the mathematics, the basic mathematical framework, and then the main content of the talk are actually two case studies, trying to give you two examples of how mathematics can actually contribute to real practical liquid crystal sort of applications or experiments. So that's the plan of the talk. It's actually not too long. I'll be on time. So the first question, the first and foremost question is, what are liquid crystals? So liquid crystals, as the name suggests, they are somewhere between liquids and solids. So they're effectively materials which are more ordered than a liquid, but less ordered than a solid. So if you look at the slide here I have a picture of a schematic phase transition between an isotropic liquid, which is a normal liquid like water, and a crystalline solid. So the liquid is the phase at the bottom left, and the solid is the phase at the top left, and you can see that the transition proceeds via two intermediate liquid crystalline phases. So the liquid crystal phases are on the right, and these are the intermediate phases between the liquid and the solid. And this phase transition, at least in this case, is induced by slowly decreasing the temperature. So you take a liquid and you slowly freeze it. You know, if you freeze a liquid, you get a solid, but if you do it very slowly, then for some materials, not all, you are going to get some intermediate liquid crystalline phases, and that's all you need to understand. So then the question is, where does this intermediate or partial ordering come from? So why are liquid crystals somewhere in between solids and liquids? So I don't think anybody has a good answer, but a common hypothesis, and this is experimentally verified, is that liquid crystal molecules, the molecules of a liquid crystal material, they tend to be asymmetric in shape. So they're either the shape of a cylinder or a disc or maybe a banana shape, but they're usually anisotropic molecules. So there's asymmetry in the molecular shape itself. And as you can expect, this molecular asymmetry, this manifests in the macroscopic properties of the liquid crystalline phases. Now there are many different kinds of liquid crystals, right? There's a hierarchy of liquid crystalline phases, but the three commonly studied ones are nematic, smectic A, smectic C, and cholesterics. So the usual three categories are nematics, smectics, and cholesterics. Nematics are usually the least ordered, cholesterics are somewhere in between, and smectics are the most ordered. So just think of this phase diagram. You have liquids, nematics, cholesterics, smectics, and then full solids. So the nematics, cholesterics, and smectics are somewhere in between, and they are the liquid crystalline phases. So I mainly work on the simplest kind. So I really only work with nematic liquid crystals. So for the rest of this talk, you will only need to remember what a nematic liquid crystal is. You don't need to worry about smectics or cholesterics. So nematics, the word nematic is actually Greek for thread. And so what really are nematic liquid crystals? I think the most sort of, the generic description is that nematic molecules are typically cylindrical or rod-shaped. So they're usually perhaps like this, but only a bit shorter, much shorter. They're on the nanoscale, but they usually have the shape of a cylinder. And these molecules, they would flow about freely as in a normal conventional liquid, but whilst flowing, they tend to align along certain locally preferred directions. So these are usually liquids with certain preferred or distinguished directions. So these are anisotropic liquids or liquids with special directions. But the key point here is that this nematic order, this concept of orientationally ordered liquids or liquids with directions or liquid-like materials which have some preferred directions is actually quite generic in nature. It's not a rare concept, it's quite popular. You find it at all levels. You find it in biological molecules, you find it in your cell cytoskeleton, you find it in human DNA. More commonly, you find it in microparticles, you find it in colloidal suspensions, granular media. And last but not the least, I'm sure you've heard of a liquid crystal display. So nematic liquid crystals are the working material of choice for the multi-billion-dollar LCD industry. So they are the working material of choice for, in some cases, your laptops, some watches, thermometers, even television screens. So they've been a huge success for optoelectronic devices. So the next question is, what makes nematic liquid crystals so popular? So why have they been so tremendously successful, especially in the context of the display industry? So I think the key word here is anisotropy, the fact that these are liquids with certain special directions. And if they have special directions, that means that they can couple, they respond very strongly to external stimuli. And what do I mean by external stimuli? Actually, Panos, your colleague here, knows more about this. When I say responding to external stimuli, I mean responding to external electric or magnetic fields and light. So the two key responses are light and responses to external electric or magnetic fields, and of course then to temperature and thermal effects. But because they have such a strong response, because they couple so strongly to these external effects, the key point is you can use this response or this coupling to control their optical or their electromagnetic or their mechanical properties. You have much greater control over their physical properties, and it's precisely this control, this sort of orientational order, the fact that they have these special directions and they couple very strongly or they respond very strongly to external stimuli. These are the two key reasons that make them the working material of choice for this huge array of technological applications. Now, liquid crystals, they were actually discovered by accident. They were discovered way back in 1888 by an Austrian biochemist. His name was Reinitzer, and he was actually just playing around with cholesterol. So he took a solid cholesterol sample and he started to slowly heat it. And what he found is that he found an intermediate hazy turbid liquid which he did not recognize. So he started off with a nice solid cholesterol sample and he started heating it, and he was expecting to see the nice clear liquid. But that did not happen. He saw an intermediate hazy turbid liquid, which at the time he did not recognize, and this was the first experimental observation of a cholesteric liquid crystal. The intermediate hazy turbid liquid with the unusual optical properties was actually a cholesteric liquid crystalline phase. And then I have a bit here about the history and the milestones. Well, this isn't so relevant for this talk, but I guess I wanted to point out that the first 40 years or so were really just devoted to finding liquid crystalline materials or materials which can exhibit liquid crystalline phases. So the first 40 years were really of scientific discovery. They found more than 200 materials which are, in principle, can demonstrate liquid crystalline phases. Then there was a dormant phase where not a lot happened because people probably weren't quite sure about how to use these liquid crystalline materials. And then you had the huge commercial revolution when people found the display application for nematic liquid, primarily nematic liquid crystals. Which is why nematics are also the most widely studied, because they have found the maximum applications in modern industry and technology. So let's now move on to the mathematics of liquid crystals. So what do you actually need for a viable mathematical theory? So many of you will know that, so nematic liquid crystals, they're complex systems, right? They're anisotropic liquids and they're complex systems, so you can clearly model them or mathematically or study them at different scales. So for example, here at UNAM, you have people who do full molecular dynamics. They study the properties at a microscopic level. They try to understand how atomistic and molecular details manifest in macroscopic phenomena. But then you have mathematicians like myself who adopt a continuum approach. So they really mathematically study macroscopic theories, where we kind of lose all the microscopic information and we have some sort of average description of nematic liquid crystals. And these theories have been hugely successful, right, in the community, in the modeling community. So it's a good investment. So what are the key ingredients of a viable continuum macroscopic theory, the sort of things that I work on? So the key ingredient is, first you need a measure of partial order. Because remember, nematic liquid crystals are partially ordered liquids, right? They're somewhere between solids and liquids, so they're partially ordered. So you need a well-defined macroscopic order parameter that is somehow a measure of this partial order. Second key component is that any viable theory should be able to describe the disordered to ordered transition. It should be able to describe ordered transitions. How do you actually make this transition from an isotropic liquid to a nematic liquid crystal and then to a solid? It has to be able to describe phase transitions. The third key component of my approach, or the sort of the continuum modeling sort of community, is that you must have the concept of a liquid crystal free energy. So a measure of the energy that is stored in a nematic liquid crystal configuration, because the hypothesis, the key modeling hypothesis, is that energy minimizers correspond to experimentally observed states. So when we try to mathematically model a system, we typically look for energy minimizers, and the claim is that these energy minimizers should mimic or reproduce or at least model the experimentally observed states. And then the fourth criterion is that any viable theory should be able to describe how nematic liquid crystals couple to external stimuli. And this is where some people at UNAM, namely my host Panos and maybe some others here at UNAM, they actually have substantial experience. How does a nematic liquid crystal actually couple to external stimuli? And then, of course, the theory has to describe equilibrium phenomena, so the sort of states that you might observe in an experiment, and also non-equilibrium phenomena, which is equally important. How do you actually switch between different observable states? So both the statics and the dynamics are equally important. So you need all of these key ingredients for a viable continuum macroscopic theory for nematic liquid crystals. Now, I will talk about the mathematics, but what I really wanted to point out in this slide is that even at this continuum level, which is really it's the least refined description, right? It's the description that ignores all microscopic level details. You still have three different continuum theories. You have the simplest O-Saint-Frank, then you have the Erickson theory, and then you have the powerful Landau-Dijen theory. And the Landau-Dijen theory has been immensely successful. In fact, it was one of the reasons for awarding Dijen the Nobel Prize for Physics in 1991. And this is to date one of the most powerful continuum theories for nematic liquid crystals in the literature. And I will be talking more about the mathematics later in the talk, but this is just to tell you that these theories have been hugely impactful. Now in terms of, so then you could ask me the question, well, okay, liquid crystals, it sounds like physics and engineering and chemistry. So why should a mathematician like myself, because I'm an applied mathematician, I was trained as a mathematician, why should a mathematician like myself and others, why should we effectively spend our careers studying liquid crystals? And the answer is actually because the mathematical theory for liquid crystals is very rich, purely, even from a purely mathematical point of view. If you were to completely discard applications and say that I'm just going to do mathematics, so then even so, the mathematics of liquid crystals is a very rich source of challenging, non-trivial, non-standard mathematical problems, which are actually, they intersect many different branches of mathematics. So even for a pure mathematician who doesn't care too much about the physics or the applications, you start working on liquid crystals, you come across cutting-edge problems in PDEs, calculus of variations, algebra and topology, sort of real pure mathematics, geometry, dynamical systems, and of course scientific computation and numerical analysis. So even from a purely mathematical point of view, the landscape is extremely rich. And of course, if you can then integrate the mathematics with applications, which is what I try to do, then it really is a very lucrative field of research. So if there are young people in the audience, I think I would strongly encourage them to work in this field. And then the question is, what can mathematicians actually contribute? What can you actually effectively do? And hopefully you will see this in my talk when I present my case studies. Well, mathematics is actually quite good for predictive modeling. You can actually make quantitative predictions, in most cases qualitative, but in some cases actual real quantitative predictions about the real pattern formation or the states that you might observe in an experiment. And that is very useful from an experimentalist's point of view, or even from an industrial researcher's point of view. You can make real predictions. The second key area is you can talk about defects. So nematic liquid crystals are often, so when you look at a nematic sample under a microscope, you will often see these thread-like structures. So this is a picture lifted from the web. Typically Oleg Lavrentevich, who's a top-notch experimentalist at Kent in the States. But you will typically see these optical imperfections, which are actually defects in the nematic sample. And these defects are poorly understood. Even though they see them all the time, they are not well understood. And mathematics can go a very long way in giving a very sound theoretical foundation for these defects, and I've done some work to this effect. So now let's talk about the two case studies, and hopefully you will see how mathematics actually contributes. So this is a 2D liquid crystal device. This was first reported in a paper by Sakanas, Davidson, Brown, and Mottram in 2007. It was an experiment with some commercial potential. So there was some potential for commercial applications. But the reason people liked it very much is because the geometry is actually very simple. So if you look at the picture, this device is really very simple to understand. It just consists of a three-dimensional, 3D array of periodic square or rectangular wells. So it's a very simple geometry, just a square or a rectangular well filled with nematic liquid crystals. I mean, that's really the simplest thing that, okay, maybe I should not say the simplest, but it really is quite standard. You're just looking at square or rectangular wells filled with nematic liquid crystals. Now, what are the other key features of this geometry? They're pretty shallow, which means that the height of the well is very small compared to the cross-sectional parameters. So when you're a mathematical modeler, this is important. You'll see why in a minute. But from my point of view, these are shallow wells where the height is small compared to the cross-sectional parameters. And the third key point is the choice of boundary conditions. So anybody who works with confined nematic liquid crystalline systems will know that boundary conditions are actually crucial. What the nematic molecules do on the boundary, it plays a crucial role in shaping what you actually see in an experiment. And the boundary conditions for this particular device were tangential or planar. Or at least this was what was reported in the paper. And what does this mean? This means that so if you have a well will have 6 surfaces. Agreed? A 3D well will have 6 surfaces, top, bottom, and 4 lateral surfaces. Agreed? 6 surfaces, top, bottom, 4 lateral surfaces. And the planar boundary conditions mean that the molecules in contact with these surfaces, they have to be in the plane of the surface. That's what tangential or planar means. If you're in contact with the surface, the molecules have to be in the plane of the surface. So how did we actually model this device? Well, I should firstly point out that some modeling was already done in this paper by Sakanas, Davidson, Brown, and Mottram, and we are building on their work. Now, if you go back to my first statement, I said that the wells are shallow, which means the height is small compared to the cross-section. So the first modeling assumption that they made, and that we've also made, is that we're effectively going to treat this as a 2D device. It's not 2D, it's not 2-dimensional, it's 3-dimensional. But because the height is small, we're going to think of this as being a 2D device, and we're going to restrict our attention to what happens on the bottom cross-section, on the bottom square surface of the well, and we're going to assume that the profile is invariant across the height of the well. So in terms of modeling, we're only going to model what happens on the bottom surface of the well. That's point number 1. Now, let's think about the boundary conditions. I said we have planar boundary conditions. So the first immediate consequence is that if your domain is now the bottom surface of the well, so remember now you're restricting all your attention to the bottom surface of your 3D well, and that's where you've imposed the planar boundary conditions. So the first consequence is that all the nematic molecules have to be in the plane of the square. So we're going to assume it's a completely planar profile. But then on the edges, a square has 4 edges, but then on the edges, the molecules have to be tangent to the edges. If they're planar everywhere inside the square, and you have planar boundary conditions, then on the edges, it has to be tangent to the edges. So on the vertical edges, they have to be pointing in this direction or this direction, but they have to be vertical. And on the horizontal edges, they have to point in either this direction or this direction. But as a natural consequence, you have a mismatch in the molecular orientation at the vertices. So the main conclusion of this discussion is that you have, so there are a number of steps here. First, you've reduced, you're now working with a 2D domain, which is just a square. That's a very simple domain. Because you have the planar boundary conditions, you're assuming that all the molecules are in the plane of the square. And also because of the planar boundary conditions, you know that on the edges, the molecules have to be tangent to the edges. And because of these boundary conditions, you have a very natural mismatch at the corners or at the vertices where you expect to see point defects. Or you expect to see some sort of singularity because there is a natural mismatch at the corners. But what was remarkable at the time is that even this very simple geometry was found to be experimentally bistable or multistable. So experimentally found to support at least 2 different optically contrasting states. So that's the definition of bistability or multistability from my point of view. When a device or a geometry can support at least 2 or maybe more than 2 stable liquid crystal states in the absence of an electric field. So the point is, if you just let the system reach equilibrium, it settles into 2 or more competing stable states. The first one is what they call the diagonal state. So this was all reported in their paper. This is not new work. The first is what they call the diagonal state, and here the molecules, they roughly align along one of the square diagonals. It's quite intuitive, right? The molecules align along one of the square diagonals. And there are clearly 2 different diagonal states because there are 2 different square diagonals. So you have one diagonal state for each square diagonal. And the next one is what they call the rotated state. So here, the molecules roughly rotated by 180 degrees between a pair of opposite edges. So this is a more vertical profile. So these are experimental and numerical sort of modeling results. The rotated solution, the molecules roughly rotated by 180 degrees between a pair of opposite edges. And again, you have 4 different rotated states related by a 90-degree rotation. But what was interesting from their point of view is that both of these states have long-term stability. They're both stable without an external electric field, and they're also optically contrasting, so they have slightly different optical properties. So that's what you need for a bistable device. You need at least 2 different stable states in the absence of an electric field, and you want these states to have different optical properties, because if they look exactly the same, then that's not very good. That's not so useful. You want them to look different under a microscope. So now I'm going to proceed to what we actually did. So we modeled this device within the Landau-Dijon theory for nematic liquid crystals, which, like I've told you, is one of the most powerful theories for nematic liquid crystals in the literature. Now, the general Landau-Dijon theory, it describes the state of a nematic liquid crystal by a macroscopic order parameter, which is called the Landau-Dijon Q-tensor order parameter. And this is actually defined in terms of macroscopic quantities, like either the magnetic susceptibility or the dielectric anisotropy. But in terms of what you need to understand, it's a macroscopic measure of the degree of anisotropy in the nematic liquid crystal. So remember, a nematic liquid crystal is anisotropic because it has special directions, so it has different responses in different directions. It responds differently to external stimuli in different directions because it has special directions. And this Landau-Dijon Q-tensor is a macroscopic measure of that anisotropy. Now, if you were working in 3 dimensions, the Landau-Dijon Q-tensor is a symmetric traceless 3x3 matrix, mathematically, with 5 degrees of freedom. But here we're going to make a simplification. We're going to assume that everything is in 2 dimensions. Our domain is 2 dimensions, the nematic molecules are planar, so they're also confined to 2 dimensions. And if you make a batch of assumptions, we reduce to what we call a 2D version of the Landau-Dijon theory, for which the Q-tensor order parameter, the macroscopic order parameter, is just a symmetric traceless 2x2 matrix. And then you just have 2 degrees of freedom. So it's quite a simplification, going from the full 5 degrees of freedom in the 3D framework to a fairly simpler framework, which is purely two-dimensional and planar, with just 2 degrees of freedom. Now what can we actually do? The Landau-Dijon theory is a variational theory, so it has the concept of a free energy. And here I have a 2D version of the energy, and if you look at my formula, you will see that the energy density, which is the integrand at the top, has 2 contributions. The first contribution is what we call the bulk potential FB. Now you don't need to understand too much, but what you do need to understand is that FB depends on temperature. So the A that you see, the parameter A, is a temperature dependent parameter. So this bulk potential actually contains information about the temperature. And the purpose of this bulk potential is to dictate the amount of order present in a nematic sample as a function of the temperature. It's a nonlinear, non-convex potential, non-negative, that somehow determines the degree of orientational ordering as a function of the temperature. That's all you need to understand. And then you have the second component, W, which is the elastic energy density, and this just penalizes any spatial inhomogeneities in the system. So if you have something which is spatially varying, very inhomogeneous, the elastic energy density penalizes spatial inhomogeneities. So you have these 2 contributions. You have the bulk energy density, which somehow enforces a certain degree of orientational ordering as a function of the temperature, and then you have the elastic energy density, which penalizes any spatial inhomogeneities. And then, of course, because you have the boundary conditions, you also have a surface energy. The surface energy is just a more realistic way of enforcing the boundary conditions. So if you work with boundary value problems, you will know that you can just impose Dirichlet conditions. Mathematically, you can just say that I want my macroscopic order parameter to take these values on the boundary. But of course, in an experiment, that's not so realistic. It's very hard to tell molecules what to do, I imagine, on a boundary. How would you? So a more realistic approach is to use a surface energy, which somehow enforces these tangential or planar boundary conditions on the square edges. Because remember, we said that on the edges, the molecules have to be tangent to the edges. And this is just an implicit way of enforcing that. And then you have this anchoring coefficient W. So if W is very large, then that means that the boundary conditions are very strongly enforced. You're somehow approaching the strong anchoring or the Dirichlet regime. And as W tends to 0, that's when you start losing the boundary conditions. That's just telling you that you're in a regime where the anchoring is actually very weak. And then I have some technical details of how we solved this numerically. So we actually did this numerically using finite element methods, trying to compute the minimizers of this Landau-Dijon energy and the surface energy, and then the hypothesis is that the local or global minimizers, they mimic the experimentally observed states. And what we got is not really that surprising. We recovered the diagonal and the rotated solutions. So even though our modeling framework was and this is what you would expect from Sackernatz, Davidson, Brown, and Mottram, we recovered the diagonal and the rotated solutions. So that was not so novel. But the novelty of the work came when we started to look at how these solutions depend on the anchoring coefficient W. And that was not previously reported in the literature. So that's the novelty of the work. Looking at the bifurcation diagram or the solution landscape for macroscopic sized squares. So we are restricting ourselves to large squares, so squares which are on the micron size, because this is also consistent with experiments. In experiments, they use squares which are on the micron scale. So we are working with squares which are at least 20 to 50 micrometers wide. So these are large squares. For a liquid crystal application, if you're on the micron scale, then that's considered to be a large system. Because liquid crystal molecules are nanometers, right? They're usually about 10 nanometers long. So if you have a box which is 20 microns or 50 microns wide, then that's a large system. So we are working with large systems. And then we started to look at how these solutions depend on the anchoring coefficient W. Now as W increases, you actually get 6 different solutions. You get the 2 diagonal ones and the 4 rotated solutions. So this again is expected. This is not surprising. But as you decrease W, you lose the bistability. And this actually can be proven mathematically, but this is the novelty of the work. that there is actually a critical value of the anchoring coefficient which can be estimated numerically in terms of your geometrical parameters and other parameters in the model, such that if W is less than that critical value, the system is actually monostable. Only the diagonal solutions survive. So there are these 6 solution branches, right? There are the 2 diagonal solution branches, and then there are the 4 rotated solution branches. But if your W is smaller than this critical anchoring coefficient, only the diagonal solution branches survive. And this was the novelty of the work, the bifurcation diagram, or studying the solution landscape as a function of the anchoring strength, and this was subsequently published in PRE. The next novelty of the work was looking at the switching. How would you switch between the 2 states? And that's actually that's practically relevant because people are interested in switching in the presence of an electric field. So we use the simplest possible model, which is called a gradient flow model. So there's no real dynamics in a gradient flow model. Well, I shouldn't say that, but it's usually based on the assumption that a system sort of evolves naturally towards a state of minimum energy, or at least towards a global energy minimizer. So you start with an initial condition and you let the system relax, and the hypothesis of the gradient flow dynamics is that eventually you should reach a global or a local energy minimizer. So it's really quite a simple model, but if you look at the equations, you will see some coupling terms. So the capital E is the strength of your electric field. The theta E is the angle at which you apply the electric field. So the electric field is a 2D vector, right? The way you mathematically model it, you're thinking of the electric field as being a 2D vector, and this vector is parametrized by an angle, right? If you're in 2 dimensions, then you parametrize a vector by an angle, which is theta E. The capital E is the magnitude. And the idea somehow is that we are going to induce a transition from the rotated state to the diagonal state by applying an electric field along one of the square diagonals. Because for nematic samples with positive dielectric anisotropy, the nematic molecules like to line up with the electric field. So there's a competing effect. Once you apply an electric field to something which has positive anisotropy, for example, it depends on the material, but at least in some cases, the nematic molecules want to reorient to align themselves with the electric field. So if you apply an electric field along a square diagonal, then the molecules, or in an appropriately chosen direction, then the molecules will want to line up along that direction. So that's enough to make the molecules want to reorient themselves. And the other key feature is that we actually make the anchoring strength W different on the different edges. And the reason for that is once you have a transition, you actually have to break the anchoring on one of the square edges. So if you make the anchoring weaker on one of the square edges, then it's actually easier for the nematic molecules to reorient themselves along the weak edge. So there are 2 key features of this model. First, you apply an electric field in the right direction, and secondly, you introduce the concept of a weak edge. A weak edge is one where the anchoring coefficient W is smaller than the anchoring coefficient W because there are 4 edges, and you make W smaller on one edge compared to the other 3. And then here are some pictures. So we start with the rotated state, so you can see that the profile is it's rotated, right? It's quite vertical in the middle. And then you apply your electric field slowly, and you can see the reorientation along the diagonal. And as it's reorienting, it's also going to break the anchoring along one of the edges. Now keep proceeding. You can see a stronger diagonal alignment in the middle, so it's trying to approach the diagonal state. So compare this with what we have. We started with this. Now we've started applying the electric field. You can see the reorientation along one of the diagonals. The reorientation is getting stronger. You can also see the fact that the anchoring is broken on one of the edges, and this is the weaker edge. So the molecules, it's easier for them to reorient themselves on the weaker edge. And keep doing this. Now it's almost entirely diagonal. Proceed further. Again, it's becoming more and more diagonal. And then that was the last snapshot. So the bottom line is that using this concept of a weak edge and an appropriately applied electric field, you can actually induce this transition from rotated, so this is what we started with, this was rotated, right to something which is really quite diagonal, just using 2 simple concepts and a very simple dynamic model. So how much time do I have? 15. Okay, yeah, that's fine. So this is my last example. So this is, I think this is interesting. This is actually mathematical modeling of experiments. So recent experiments which have been done at the University of Oxford by Professor Dirk Aas. So this is joint work with Peter Howell, who's also at Oxford, and we had a graduate student called Alex Lewis, who has now defended his thesis and now has a job. But anyhow, where does this work come from? So like I say, it's fusion of mathematics with chemistry. So what happened, this was at least maybe 2 years ago, or maybe less than that, I can't quite remember. But Dirk was doing some experiments in his laboratory where he was looking at annular chambers. So what do I mean by an annular chamber? It's really a very shallow well. But remember, we were looking at square wells. So the square wells are wells which have a square cross-section. So now you can think of the same thing, but now you have an annular cross-section. So you can think of it as being a well, effectively, pretty shallow, but with an annular cross-section. But again, very shallow. And then what he found is that, and he was also using planar boundary conditions. So the planar boundary conditions means that if you look down on the well, so if you look down on your annular cross-section, the nematic molecules preferentially follow the circular boundaries. So an annulus has two circular boundaries, agreed? And the boundary conditions mean that the molecules preferentially follow these circular boundaries. So this is quite standard. It's a standard example for people who do nematic liquid crystals. But of course he was not using nematic liquid crystals, he was actually using viruses, FD viruses. But anyhow, so he did these experiments. And I think what he found surprising is that he found a number of different stable states. He actually found at least 6. There may be more, but he found at least 6 different stable states. The first state, if you look at the U state on the extreme left, is what you would naturally expect. So I told you that the molecules like to follow the circular boundaries. So the most obvious candidate is that the molecules follow the boundaries everywhere, right? They don't do anything exotic or exciting. They just follow the boundaries. So you have a nice circular pattern and completely defect-free, a nice regular defect-free, completely bent pattern. And this is what you would intuitively expect under the circumstances. So why should it do anything different? But it does. If you look at the D2 state, the D2 state actually has 2 point defects which are pinned to the outer boundary. Then, or at least they're close to the boundary, if not pinned to it. And then he did some more and he found other states. If you look at the D3 state, then you can actually see 3 point defects pinned to the outer boundary. And all in all, he had 6, at least 6. He had the nice uniform defect-free bent state, and then he was also observing states which appeared to have boundary defects, or defects pinned to the inner and outer boundaries. And his question was, to us as mathematicians, is why should we ever see states with boundary defects? Why should you see them in equilibrium? You would expect a stable state to be defect-free. There's no obvious reason for this system to have a defect, and yet he and his collaborators see stable states which have boundary defects. So why is that? Now, point number 1 is that, like I told you, he's not using liquid crystals, but because these patterns are very much like liquid crystal, nematic liquid crystal patterns, he said to us, or we thought we could actually model this using a liquid crystal approach, using one of the nematic liquid crystal theories. Because these patterns very much look like nematic patterns, these are like rods which are lining up with one another. We thought, as a first modeling approach, why not use nematic liquid crystal theories to try and describe what is happening and to gain some insight. So we did something which is really quite simple. So this time we decided to work with the simplest continuum theory. So I told you at the start that there are at least 3 different continuum theories. There's the O-Saint-Frank, and then there's the Erickson, and then there's the Landau-Dijen. But this time we decided to work with the simplest one, which is the O-Saint-Frank theory. The O-Saint-Frank theory is the simplest because it assumes that the nematic molecules they're uniaxial, which means that they have a single distinguished direction of alignment. It assumes that all the molecules, they want to line up along a single distinguished direction. And this is clearly not true, right? Most systems are biaxial. There's a primary and a secondary direction of preferred alignment, but the Ose-Frank theory is based on this assumption of a single distinguished direction. So we started to work with the Ose-Frank. Then we made the same modeling assumption that because these are very shallow wells, we're only going to model what happens on the bottom annular cross-section. So we're going to treat this as a 2D problem, a two-dimensional domain. We're only going to model what happens on the bottom cross-section, which is an annulus. So it's a 2D problem in the Ose-Frank framework, which assumes that everything, which assumes that the nematic state is described by this one special direction, which I've called n here. But n, because we've assumed that everything is two-dimensional, is now just a two-dimensional unit vector. And if it's a 2D unit vector, you can parameterize it completely in terms of an angle theta, right? And the physical interpretation of n, this 2D vector in the model, is that it represents the single distinguished direction of alignment of the nematic molecules for this 2D problem. So already you have some modeling assumptions. You're taking a 2D domain, which is an annulus. You're assuming that your director profile is strictly two-dimensional. If it's strictly two-dimensional, you can just parameterize it in terms of an angle theta. You're assuming that everything is uniaxial with constant order because we're working in the Ose-Frank framework. So effectively, your problem now is entirely recast in terms of this one angle theta, which somehow represents the single distinguished direction of molecular alignment on this 2D geometry, assuming that everything is actually planar. Now, the Ose-Frank theory, like the Landau-Dijen theory, is a variational theory. So it has an associated energy function. The most general form has these four different elastic constants, K1, K2, K3, and K4. So these elastic constants are typically associated with different kinds of deformations. But if you restrict yourself to two dimensions like we have done, so if you restrict yourself to a 2D domain and to two-dimensional director field, so there are two assumptions. It's a 2D domain and we're assuming that everything is in the plane. Your Ose-Frank energy actually simplifies. You get this formula only in terms of K1 and K3. And if you look at the formula, you can see that it's a nonlinear functional. It's pretty nonlinear, but it's purely in terms of theta, this angle theta and its derivatives, and the two elastic constants K1 and K3. And once you have this energy functional, you can write down the Euler-Lagrange equations. That's also standard. So in terms of what I've done here, the Euler-Lagrange equations are here at the bottom. And so far you'll see a parameter delta in the equations. And delta is what we call the elastic anisotropy. So it's really the scaled difference of the two elastic constants K1 and K3. So what do you need to take away from this slide? You need to remember that now our domain is a 2D annulus. We've rescaled the annulus. So the aspect ratio is what I call B. So B is the inner radius and the outer radius has been rescaled to 1. So the technical details are perhaps not important. I think you just need to remember that we have a 2D annular domain with aspect ratio B. So B is the ratio of the inner to the outer radius. And our second parameter is delta, which is the elastic anisotropy. So far we have two modeling parameters, the annular aspect ratio B and the elastic anisotropy delta. But we also have the boundary conditions to worry about. So I've already told you that at least experimentally the claim is that they have tangential boundary conditions, which means that the molecules like to follow the circular boundaries of the annulus. So then the question is, how do you mathematically model these boundary conditions? You have two choices. The first one is Dirichlet. You just tell, you prescribe the boundary conditions. You prescribe the value of theta on the inner and outer boundaries. The second option is weak anchoring, which is more realistic, is when you have a surface energy. And again, alpha is the rescaled anchoring coefficient. As alpha increases, in the limit alpha tends to infinity, you recover strong anchoring. And as alpha tends to 0, you lose the boundary conditions. So the complete model has three parameters: the annular aspect ratio B, the elastic anisotropy delta, and the anchoring coefficient alpha. Three parameters. So what did we actually do? So at the very start I told you that the most intuitive state is the bend state, the uniformly bent defect-free state. And it's also very nice because you can write down an explicit formula for this state. And once you have an explicit formula, if you work in the strong anchoring regime, strong anchoring is the reach the boundary conditions, you can actually do some stability analysis, right? And the stability analysis for me is when I look at the second variation of the energy. And so once you have strong anchoring, you only have two model parameters, right? You have the angular aspect ratio B, and you have the elastic anisotropy delta. And then we do a I would say a standard stability analysis to show that the defect-free state, which is this very nice state, this nice defect-free bend state, loses stability if the elastic anisotropy delta is bigger than this material-dependent quantity. So this is an explicit relationship between delta and the annular aspect ratio B, which indicates instability, the onset of instability of the defect-free state. And this result was actually known in the literature. Although our method was a bit different, but we actually did find it in other papers. But then we decided to include weak anchoring into the model, and this is kind of new. So now we look at the full, so now we have the full three parameters. We have delta, the elastic anisotropy, we have the annular aspect ratio B, and we have the anchoring coefficient alpha. And then we have the same mathematical strategy in that we start looking for the optimal instabilities. So when does the defect-free state lose stability as a function of these three parameters? And it's very technical, but the methodology, I would say, is standard and well established. So if you look, every perturbation eta, it can be decomposed into what we call modes. So it's a sum of modes which are labeled by this integer k. And for every mode you have a radial part, f, which only depends on the radial distance from the origin, and then you have the azimuthal part, which depends on the angle in the plane, because you're using the standard planar polar coordinate system. And when k is equal to 0, that's the purely radial mode of perturbation. But then you can solve for these optimal modes of instability, and you get some fairly complicated compatibility relations. The work is now published. These compatibility relations are between delta, B, and alpha for different values of k. Well, you need compatibility relations between delta, B, and alpha to get this instability. But once you do that, you can actually start to plot stability diagrams. So here I have B is equal to 0.1. So if the inner radius is 0.1 and your outer radius is 1, then the aspect ratio is actually 1/10. So it's a pretty wide annulus. You're looking at a pretty wide annulus. And what have I plotted here? You can see alpha on the vertical axis. Alpha is your anchoring coefficient, and your elastic anisotropy delta on the horizontal. And then you can see these curves, right? A red curve, a blue curve, a green curve, a purple curve. Now mathematically, what do you need to understand? The defect-free state loses stability as soon as you cross one of these curves. So the defect-free state is stable within this framework to the left of the red curve, and is unstable everywhere to the right. But the red curve corresponds to the k is equal to 0 mode. So what this diagram is really telling you is that the first mode of instability is always the radial mode, the k is equal to 0 mode, and the other azimuthal modes, the higher values of k, you only see them for larger values of delta and only for alpha less than 1. So the most obvious instability is the radial instability. It loses stability with respect to the radial mode, which is k is equal to 0 first. But then you can do the same for other values of b. But if you look here, so first I have b is equal to 0.1, then 0.5, and then 0.9. So 0.9 is a very narrow annulus. 0.1 is an aspect ratio of 10, and 0.9 is an aspect, it's a pretty narrow annulus. But the qualitative features are actually exactly the same. I mean, you see the red curve first. So in all cases, the defect-free state is stable to the left of the red curve and unstable to the right. And you will see that the higher modes of instability, the azimuthal modes with a non-zero value of k, they only occur for delta bigger than 0.5 and for alpha less than 1. So what's the conclusion of this study? The conclusion of this study is that if you want to destabilize the defect-free state, because one of the first questions that Dirk had is why should the defect-free state ever lose stability? And this tells you that it can lose stability either for materials which are very anisotropic, so for large values of delta, or with systems which have weak anchoring for small values of alpha. So these are two regimes where the defect-free state is actually not the optimal state. But then the question is, well, if the defect-free state is not optimal in these regimes, can we actually observe states with boundary defects in these regimes, with materials which have a large value of delta and small value of alpha? Because the second question that Dirk had was, why does he actually see states with boundary defects? So now we know that the defect-free state is not always stable, but then the question is, can you see states with boundary defects in these regimes? Those are two separate questions. So let's move on to the next question. So mathematically, trying to get states with boundary defects is pretty non-trivial. So what we did is pretty artificial, actually. So we made a number of assumptions. So remember, we have three parameters. We have delta, the annular aspect ratio B, and the anchoring coefficient alpha. So mathematically, we said, let's work with strong anchoring. So then you don't have alpha anymore. Let's just assume that we have Dirichlet boundary conditions. And let's work in the one constant case. So we set delta equal to 0. So now you're just left with one parameter, which is the annular aspect ratio. And then we said, let's partition our annulus into sectors. So if you look here, these are examples of sectors. You partition your annulus into equally spaced sectors. It's quite artificial. In a real experiment, I mean, the real experiment has the whole annulus. And now we're just looking at a sector of the annulus. And then we make a further assumption. The annulus will have four edges, right? You'll have the two curved edges, which actually belong to the real annulus. And then you have the two straight edges, which are artificial. But we imposed tangent or planar boundary conditions on all four edges. And as a natural consequence of these boundary conditions, we get four boundary defects, agreed? Because as soon as you have tangential or planar boundary conditions, you have a mismatch at the corners, and you get these artificially created four boundary defects for each of these sectors. And mathematically, your problem is reduced to actually solving the Laplace's equation, because you've set delta equal to 0. You've killed so there's no elastic anisotropy, delta is equal to 0, and you're working with strong anchoring. And if I skip all the mathematical details and you trust me, the problem reduces to solving Laplace's equation on these sectors with these tangent boundary conditions, which can be done. It's technical and it's long, but it's a computation that can be done. And once you do this computation, the next step for us was to actually glue together these sector configurations. And once you glue them together, you generate a configuration on the entire annulus. But the key point now is that this artificial configuration has boundary defects. So it's an artificial way of generating configurations which have boundary defects. But of course, once you have this artificial construction, your next step is to actually estimate the energy. But here you have a catch. Point defects in 2 dimensions have infinite energy. So we actually have to excise, or we have to remove small neighborhoods of the corners to estimate the Ose-Frank energy of these sector configurations. So again, this is a technical, I would say it's a non-trivial computation. But it can be done. And at the end of the day, you produce expressions for the energy that depend on only 2 factors. Because remember, there is no anisotropy. You've set delta equal to 0, and you're working with strong anchoring. So these energy expressions only depend on the annular aspect ratio B, and also the number of sectors that you've introduced, which is capital N. So you have these energy expressions, which depend on the number of sectors, and they depend on the annular aspect ratio. And then the next thing is you start comparing the energies of these artificial configurations. I have made no claim as to whether these are actual solutions of the Euler-Lagrange equations. I'm just going to compare the energies of these artificially constructed configurations with boundary defects with that of the defect-free state. Because my aim is to identify certain parameter regimes where it might be energetically preferable to have configurations which have boundary defects. So here, delta is equal to 0, so it is so no elastic anisotropy, and you compare the energies of the defect-free state, and then you compare the energies of the state with just one sector, so maybe 2 boundary defects, and then a state with 2 sectors, so maybe 4 boundary defects, 2 on the inner boundary, 2 on the outer boundary. But if you compare the energies, you see that the defect-free state, which is the nice bend azimuthal state, almost always has lower energy, except for when the annulus actually approaches a disk, except for when your aspect ratio approaches 0. But when your annulus approaches a disk, that's when some people would argue that the Ose-Frank theory is a continuum theory, and you shouldn't really be making comparisons in that regime. Because if your aspect ratio is very small, that's actually is somehow approaching a vortex at the center, and point defects of infinite energy in 2D. So I would say this regime of very small aspect ratio is perhaps not so physically relevant even for the experiments. So this is not giving much insight into the actual experiments. But now, numerically, so when the analysis relies on delta is equal to 0. So the analysis, all these constructions, they use the fact that delta is equal to 0. But numerically, you can work with non-zero values of delta. So then we introduce elastic anisotropy back into the model. And now you see a clear regime for actually macroscopically relevant values of your aspect ratio, for macroscopically relevant annular domains, where your defect-free state has higher energy than competing configurations with boundary defects. So this is physically relevant. You've identified a range of aspect ratios which are physically relevant with strong elastic anisotropy, where the defect-free state actually has higher energy than competing configurations. And here I think is what we have a nice phase diagram. I like this phase diagram very much. Is when we have delta on the vertical axis and we have the annular aspect ratio on the horizontal one, and we compare the energies of the defect-free state and these two states, U2 and U2 with n is equal to 1. So these are states with boundary defects. The green and the blue are states with boundary defects. And we identify the state, so we compare the energies of these 3 or 4 competing configurations, and we identify the state which has minimum energy in this restricted class, and the colors sort of identify the particular state. And again, if you look at this picture, you will see that there is a distinct region where the red and the blue are actually energetically the optimal within this restricted class. So if you compare the energies of these 4 configurations, the green and the blue are the states which have boundary defects. They are actually energetically the preferred ones for those ranges of delta and rho. And this is practically useful information. This is giving you precise information about where to expect states which have boundary defects in terms of delta and rho. And then we've done the same with weak anchoring. So now we've killed delta, so now this is delta is equal to 0. So here we were varying delta and rho with strong anchoring, and now you get rid of delta, you set delta back to 0, and now you have alpha back into the model, which is the weak angle, which is the anchoring coefficient, and you produce a similar phase diagram with alpha on the vertical axis and the annular aspect ratio on the bottom. And again, you see there's a pretty well-defined region, the green and the blue regions, where these artificial configurations with boundary defects, they have lower energy than the defect-free state. And again, you're giving Dirk or you're giving these experimentalists real information about where they might be able to find states which have boundary defects, because that was the question. But then you still have one pressing last question. This construction is is artificial. You know, me looking at a sector, trying to construct solutions of the Laplace's equation on a sector, and then just gluing together solutions along the common edges. So, you know, then the pressing question is, does this artificial construction give us any real insight into real solutions of the model? Now, that's a hard question. But one approach is to use a gradient flow approach. So this is a toy gradient flow model, but the idea is that we use initial conditions which are constructed from these sector solutions. So use a gradient flow model, which is some sort of a dynamical model, and it's based on the principle that eventually, given any initial condition, the system should relax into an actual stable equilibrium. That's the hypothesis, that given an initial condition, it should relax into a stable equilibrium. So we take the equations, and the initial conditions, they are constructed from our sector solutions. So the initial condition is dictated by our sector solutions, which have these boundary defects. And our claim is that if the final solution, that's after it's kind of relaxed, if the final solution retains these boundary defects, then the claim is that our sector solutions do a pretty good job of actually mimicking real solutions which might exhibit these boundary defects, or defects which are perhaps not pinned to the boundary but perhaps very close to it. So this is what we start off with. Look at the initial condition. So this is strong anchoring. Alpha is almost 50. So this is almost when you have very strong anchoring or Dirichlet conditions. You start with an initial condition which does have boundary defects, 2 on the inner boundary and 2 on the outer boundary. And then you let the system relax. And if you look at the final solution, that's actually your defect-free bend state, the one which is E. The plot E is your nice defect-free bend state. So you've actually lost the boundary defects. But this is not surprising, right? Because with strong anchoring, the states with boundary defects have higher energy than the bend state, than the defect-free state. So it's not surprising that an initial condition with boundary defects actually relaxes into something which is defect-free. But you can repeat the same numerical experiment with weaker anchoring. And if you do that, you see from these plots, so this is all weaker anchoring for smaller values of alpha. So the one before had alpha is equal to 50, this is strong anchoring, and now you have alpha is equal to 10, which is pretty weak anchoring, alpha is equal to 30, alpha is equal to 40, but you see that the boundary defects actually survive. With weak anchoring and exactly the same initial condition and the same dynamical model, but just with weaker anchoring, the boundary defects are not dissipated, they actually survive. So when we use an initial condition which is constructed from our artificial sector solutions with these boundary defects, you use them as an initial condition in a numerical solver, and you let the system relax. The boundary defects still persist after a long time. And this is what Dirk actually sees in his experiments. And that actually brings me to the end of my talk, so I'd like to thank various people who have given me some money and support. And I'd like to thank you for your attention.
Questions? Design theory. Why here uses what's in front as opposed to design?
So that's a perfect question. We can use the Landau design. We have used it in a subsequent paper. The Osen Frank was a mathematical sort